Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class. I'm putting it online though in case it would be helpful to others as well. In the first part of this video, there is a link to a printable set of guided notes that you can access if you would like to use them to follow along with the examples that I'm going to do in the video. In that first video, we discussed 6 basic important rules to know for differentiation. What we're going to do in the second video is talk about some other pieces for derivatives that is important to know as you move forward in your study of calculus. So, right, let's jump back into the notes to this section where we have some extra stuff to know. The first little extra piece that we're going to talk about in this video is looking at a function and being able to determine where are its horizontal tangents. Now, before we discuss what's in the box there or the example, I just wanted to show you a little visual representation of what I'm talking about here. So, we have a nice curvy graph, and what you can see are at all of the red turning points, right? We called those turning points a couple of sections ago. At those red turning points, if we were to draw a tangent line, the tangent line there would be horizontal. I drew one of them in. I might be able to do another one. Yeah, look at that. Maybe. Maybe not. I am making a mess of this thing. There we go. I'm not going to waste our time doing any more than that. But as you can see, at these turning points, the tangent lines that we would draw at all of them would be horizontal. Okay. Now, that's going to come in handy to be able to look at a function and figure out where it has the turning points, where it has the horizontal tangents. It'll come in handy later on when we start to talk about some pretty cool applications of derivatives. Okay, I'll give you a little hint. These horizontal tangent points are occurring at maximums and minimums, right? Sounds super exciting, right? I love it. I don't know if you're going to, but that's where we're going in chapter 4. For right now, we're going to stick with some basics, and that is looking at a function, and maybe without graphing it, maybe not necessarily graphing, could you just look at this function and say where its horizontal tangents are going to be? Yes, we can. It's pretty easy too. Okay, first of all, the if so, where question, meaning if there are horizontal tangents, where are they? What we're going to identify are just the x coordinates where they're happening, meaning where they occur along the function's domain. Okay, so it's a pretty simple process as long as you remember this. The slope of every horizontal line is 0, right? And that translates for us into a y prime value of 0. So looking at our function y equals x to the 4th minus 2x squared plus 2, if we take the derivative using, some very simple rules, the derivative of x to the 4th is 4x cubed. The derivative of 2x squared is minus 4x. The derivative of the plus 2 constant term goes to 0. And then we sub 0 in for y prime, okay? Or sometimes, we say we're setting the derivative equal to 0, the derivative expression equal to 0, and solving to find our horizontal tangents. That's what we'll find. This one's pretty easy to solve by factoring. Factor out a greatest common factor of 4x. If you want to continue factoring the x squared minus 1 into a difference of squares, that way you don't forget Plinus, you could do that. You could also solve by adding 1 and square rooting from this step. But either way, we're setting each factor equal to 0 and solving for x. We get x equals 0, x equals negative 1, and x equals positive 1. Those are the points along this function's curve that would have horizontal tangents. That's all. Okay, so like I said, basics for now. You're just going to be asked simple questions like, does this function have horizontal tangents? If it does, where are they? And this is the process that you're going to take. We will do a lot more with this later on when we move into applications of derivatives in chapter 4, like I said. Let's move on. Some more extra stuff to know. This one's really fun, actually. It's fun with basic functions, at least. I think it's fun for all of them, but you might disagree as we keep going. We'll see. All right, so when you have y equals and then an expression in terms of x, let's say, I like to call that the original function, or you could just say that's your function, right? And then when you take its derivative, we can call that y prime or dy over dx, okay? However, what we're now going to say is that that's the first derivative. Because actually, you could take a derivative many, many times as you need to do whatever it is you need to do with your function. So you could have something called y double prime, or I just say the second derivative of y instead of trying to read all of that in some way that would make sense. Okay, this is just another notation for second derivative. And how you get a second derivative is by going to your first derivative and differentiating it. You could have a third derivative, y triple prime, or we just say the third derivative value. We could have a fourth derivative, and actually so on. We should probably put dot, 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 because it could keep going. Now notice that after the third derivative, we no longer use the apostrophes to denote, because that would just get a little ridiculous. So you can use Roman numerals in parentheses like this. You can use just the number of the derivative in parentheses like that, or you can use this notation. There's some other pretty cool notations out there, by the way, like I think this is Newton notation maybe, where you use dots to denote your derivative. We don't really do that here, but I had one student last year who did it, and I allowed it. Okay, so all different options to denote derivatives, but they all mean the same thing. All right, so I said these are fun because for a simple polynomial like this, the derivative will eventually just go to what? What do you think? Let's see. Y prime of x cubed minus 5x squared plus 2 is 3x squared minus 10x, right? Let's differentiate again. Y double prime is 6x minus 10. Now, keep in mind, I probably should have read this. We're doing the first four derivatives, but do you see what's going to happen? Can you predict what will happen for that fourth derivative? Y triple prime, the third derivative, is just 6, right? The slope of 6x minus 10 is 6. And finally, the fourth derivative, which I will denote like this, is 0. And that is characteristic of simple polynomial functions where, you know, all of your powers are positive, integer values. Okay, if you take the derivative so many times, it is going to go to 0. It's not going to happen for every single function, though. Let's take a look at the u-try. This says find the second derivative for these functions. Okay, let's take a look at an example. Oh, I called it a u-try. It's not a u-try. That's great because I'm going to do it with you anyway. Let's take a look at example 7a. Y equals 1 over x is the function here. And actually, the first thing I'm going to do is just rewrite that original function as x to the negative 1 power so that we can see here that clearly the only thing we need to use to take a derivative is power rule, right? This is a quotient. If you kept it as a quotient, you should use quotient rule. However, that's a little overkill. You could just do a simple rewrite, and now it's just a power rule. Now let's take the first derivative, which I will denote this time as dy over dx. Not that the notation necessarily matters here, but I'm just sort of following what the directions are giving me up here. And that derivative is negative 1x to the negative 2 power. Go one more time, and I would suggest just leave your first derivative in this form. Even though negative powers look, kind of messy, that's all right. It's best to leave it like that because then it's an easy power rule again to get your second derivative. So the second derivative, the negative 2 will come down and multiply with the negative 1, making the coefficient positive 2. Bring along your x, subtract 1 from the power to get the new power, and that gives you a negative 3 power. Again, you could leave your answer like that. It's fine. Or we should note that the other way that you could denote this derivative, this second derivative, is as, not negative, sorry, 2, I was about to do another derivative. That's actually what I was doing in my head. We're just rewriting though. Second derivative, 2 over x cubed. Something stopped working for a moment. Ooh, there it is. Okay, here's another one to try. If you feel like you got the hang of this, pause the video, try it for yourself, and then come back. A square root function is the same as a 1/2 power. So again, I'm setting it up as a rewrite of the function first. And then I'm taking a first derivative using power rule. 1/2 x to the negative 1/2 power. The 1/2 minus 1 part goes to negative 1/2. Leave it like that to get a second derivative. And again, just power rule. The negative 1/2 will come down and multiply with the 1/2 that's already there and make a negative 1/4 coefficient. Bring along the x. Take negative 1/2 minus 1. It's like negative 1/2 minus 2 over 2, which is negative 3 over 2. And there you have it. Or you could write that as negative 1 over 4x to the 3/2. Change that negative power to a positive. You could write it as negative 1 over 4 times the square root of x cubed. I'm not going to do all that. This is good enough to say we're done. Okay? So keep in mind that that's a thing that's out there. You can take a first derivative, second derivative, third derivative, and so on, and you'll see applications of that actually very soon. In the next section, we're going to start to talk about a little bit of physics applications, and you'll see where taking a first, second, and even a third derivative will come in handy. Finally, in this last part of the extra stuff to know for this section, we are going to see a couple of problems where we need to use derivatives. Okay, what we need to keep in mind as we're working through these last couple of examples is that they're basically here to help us practice using the correct rules that we have learned. And something else that we're going to see in the last problem is how we can use derivatives to denote rates of change. Okay, but let's start with a pretty simple example. Example 8. All right, so in example 8, we just have let y equal u times v, uv, be the product of the functions u and v. Find y prime of 2 if u of 2 is 3, u prime of 2 equals negative 4, v of 2 is 1, and v prime of 2 equals 2. All right, so basically what you need to know here is that y could be considered a function of x. Okay, y could be considered a function of x. And the x value that we're looking at in particular is at x equals 2. We don't know what particular function y is here. It is just shown to us as a product of two differentiable functions that are being called u and v. So this could be like maybe x times x cubed plus 1. Who knows? It doesn't matter. Well, let's call it mystery functions. Okay, we don't know exactly what particular type of function we're working with here, but that doesn't matter because we can still do what we need to do given the fact that we know that we have a product and we are asked to find a derivative. A product with finding a derivative means we need to use product rule. Okay, let's try to write legibly. Sorry. Use product rule. That's what that says. And let's use that cute little jingle thing I have for us. 1d2 plus 2d1 is how we easily remember the product rule. First times derivative of second plus second times derivative of first. That's too much to say. 1d2 plus 2d1 has a nice little ring to it. All right, so here's what we're going to do. Let's start with our function. Y equals u times v. And let's show that we can find y prime. Don't worry about any numbers yet. Okay, let's just show the derivative of u times v with the product rule. Y prime is going to be 1, don't write 1, write u, that's the first function. D2 is v prime, this is 1d2, plus 2 is v, d1 is u prime. And there you have it. There's the formula that you need to use to calculate the derivative of this product. Now, in particular, at 2, that means go up here to these values and fill them in. U at 2 is 3. V prime at 2 is 2. Plus V at 2 is 1 times U prime at 2 is -4. 3 times 2 plus 1 times -4 is 2. Ta-da! Woo! There's our answer. All right, I'm going to admit, this example was not super exciting, right? It's just doing a rule and plugging in values, but it's here to just remind you of the basic rule that when you have a product of functions, to find the derivative, you use product rule. Now let's look at one that's like a lot more fun. And we're going to, what you're going to see eventually, there's a lot of words there, right? Math class, but we have lots of words. What you're going to see is once we get through all of these words and we turn them into some mathematical notation, we're going to see that we're actually going to be doing basically the same thing that we just did right here. Okay? We just have to sort through it all to figure out how we can get it to that point. Let's take a look at it together. This one's fun. I love teaching this one. An orange farmer currently has 200 trees, yielding an average of 15 bushels of oranges per tree. Now, I'm going to stop you right there, and I'm going to tell you, before I started teaching this class and this particular problem, I really didn't know what a bushel was. Okay, I had to look it up. You want to look it up? Don't mind all those tabs. What is a bushel? What is a bushel of oranges? Let's be very particular here. See that? A bushel is approximately 48 to 72 oranges, or 32 to 48 grapefruit. Okay, so there you go. That's how many oranges you're going to get out of a bushel. Not that you necessarily needed to know that, but it kind of makes it more fun if you actually know what you're talking about here. All right, she's expanding her farm at a rate of 15 trees per year. That means that she has 200 trees right now, but every year she's adding about 15 more trees. Okay, I love this part. While improved husbandry is improving her average annual yield by 1.2 bushels per tree. Okay, this is another thing I'm going to admit. Husbandry, never heard that word until I started teaching this particular problem. Let's Google it. I was like, does that mean, okay, husbandry. Like, I mean, I see the word husband in there. Improved husbandry, improve the husband. No, that's not what it means. It means the care, cultivation, and breeding of crops and animals. That's what husbandry means. So she's improving the care of her farm, which means that her trees are doing better. They are improving their average annual yield by 1.2 bushels per tree. So the question is, what is the current instantaneous rate of increase of her total annual production of oranges? Okay, so how are we going to get to a point where we're doing this, right? That's a big question here. How are we going to get to that point? Well, we're going to write an equation. That's how we're going to get that to that point. How are we going to write an equation? We're going to write an equation by defining variables. Okay, so very simple algebra stuff. Let's define some variables. An orange farmer currently has 200 trees. However, there's going to be more, right? Because she is planting more trees. So there's a variable. Let T equal trees. That's just how many trees she has. So eventually we'll plug 200 in for T, because that's how many she has right now. Every tree gives an average of 15 bushels from it. Okay, so, but that's also increasing, right? That's changing. So there's another variable. What did for some reason, I used Y for yield per tree, but that is standing for the bushels. I guess we should just put a little note here. It's in bushels. Okay. Now, there is one other variable involved, and that is the total production. Okay, the total production here would be, she gets 15 bushels per tree times 200 trees, right? Would give her her total production right now. So I'm going to say one more variable that we should define is P for production. And that is, what am I trying to say here? A total. So we should be able to write a simple equation from these variables. What would that equation look like? The production comes from the number of trees she has times her yield per tree. All right, now we at some point have to acknowledge that what we should be doing is a derivative. Okay, and there's two reasons for that. Number one, we are in a section in calculus where we are finding derivatives, right? So we should be doing a derivative at some point. But a better reason, here's the other reason, is because we are being asked for the current instantaneous rate of increase of her total production of oranges. We're asked for a rate of increase in the production, which means what we are actually trying to find or calculate is a P prime value. Okay, rate of production is not P, it is P prime. A derivative can represent a rate of change. So there are some other prime values that we should acknowledge as well, though, here. So I'm going to start to write a little bank of information. I currently know that there are 200 trees and that the yield per tree is 15 bushels. Okay. However, I also know that she's expanding her farm at a rate of 15 trees per year. That is a rate of trees, T prime. And it's equal to 15. While improved husbandry is improving her annual yield, okay, by 1.2 bushels, change in the yield is 1.2. So now we have a ton of information that will be helpful for whenever we need to go and calculate P prime. Before we can use that information, though, we need to just get a formula for P prime, and that's where we are once again. Here we are at the point where we are just doing what we did right here. We are just finding the derivative of T times Y using the product rule. 1d2 plus 2d1. And then using the known information, subbing in 200 for T, 1.2 for Y prime, 15 for Y, and 15 for T prime. And we will calculate that to be, I'm going to look at my answer key, 465. Now, what is it? Well, it's total bushels, right, per year. Because it is a rate, we should add that per year piece. And what this says is that she is actually going to get 465, she should get an additional 465 bushels every year based on how she is expanding her farm per year. Yay, that one was more fun. I hope you thought it was fun too. That's it for this section. As usual, I hope this was helpful. Bye.